Okay, this is the lecture of finite element. 2 credits. I am the instructor. Uh, this course aims to enable the students to understand the basic concepts and procedures of the finite element method. So I'm not going to teach you how to use a software. Okay, here, for example, how to use a SAP 2000 software because there's in another course. Okay, here the emphasis is I'm going to explain how the finite element works rather than how to use a software. Okay, here is the outline of the lecture. First, I'm going to give presentation about overview of the finite element method, and then after that we are going to discuss the direct stiffness method applied to simple problems, the simple problems of spring systems and bar structures. And then after that, we are going to apply the direct stiffness to a more difficult problem. That's two-dimensional truss and three-dimensional truss. Okay, that's we emphasize for the direct stiffness method, both manual computation as well as computer computation programming. I mean, after that, we are going to look into the details of the formulation aspects of the finite element method. We have a simple model actually. That's one-dimensional elements for the bar axial deformation problem, and then we want to formulate this the finite element for this problem using the simplest element. That's the north bar element. Actually, there are several types of elements possible for this problem, but we are learning the simplest one. This covers the teaching materials before the mid-semester exam. After the mid-semester exam, I think we still on the topic of number 3, and also lastly about the topic solving 2D problems, specifically plane stress or plane strain problems using the simplest element. That's constant strain triangle element. Most of the time we will discuss this. If we still have time, however, in the end of the semester, this is we are going to discuss another types of element. Okay, but this is not the main teaching materials. I mean the in the curriculum up to this element. This is if we still have time, I just maybe introduce a little bit, just a brief introduction about this element. Okay, that's all about our course. Regarding the references, this is the references you can use for this course. This is the book that I wrote, just finished this year. Okay, it's a long time already. And then this is also the two good books, I think, for first-time learner of the finite element method from Logan and Hutton. Basically, these books have many similarities, but in my book, there are details computer implementation. Okay, in these two books, there is no computer implementation. Uh, Also, there is one good internet resources for learning introduction to finite elements from Professor Carlos Felipa. You may download the teaching materials from this website. So I think that's the references that you may use for learning finite elements for the first time. Okay. If you want to read more advanced reference, advanced book, a little bit advanced, not too advanced. That's this famous books, I think, very famous. Many universities use this concepts and application of the finite element analysis. The book that I know up to now is up to up to the fourth editions. Okay, and there is one book specialist for structural analysis by Weaver and Johnston. It's an old book, 1984, but I think it's still relevant for structural analysis and still good. Okay, so I included in here, but this is a little bit advanced. So there are some uh, materials that quite advanced, not too advanced, okay, not too advanced, but yes, for maybe for the first time learner, a little bit difficult. So that's about references. Finite element generally is a method for computer applications, so not for hand calculations like moment distribution or cross method or slope deflection or maybe what Clapeyron. That's for manual structural analysis. But finite element is a general method for computer application, so it's not suitable for hand calculation. Even though for simple structure, in order to understand the procedure, I think it's good to going over for the uh, to compute the to analyze the structure using finite element. But in general, we should use programming language to implement the finite element. So this is the MATLAB. I use MATLAB. This is the version of MATLAB I use to implement the finite element method. Okay. All teaching materials I will upload in cloud, including the assignment if there is, okay, including the exam. So please, you have to be updated by accessing these websites. Okay. Regarding how I will give you grades or gradings, this is the weights, grading weights. I will grade you from your homework assignments. That's the weights 30%, and then mid semester exam with the grading weights 30% as well, and the final exam 40%. I hope all you get excellent grades, A plus. Okay, can you? Okay, I think you can
No, sir.
by
The
working hard.
maximum
Okay.
grade is A.
Oh, maximum
There's no
A.
A plus.
Okay, just kidding. Okay. Uh please come on time. Okay. Uh Normally I will start on time except today because of the conference. If no, I will tell you in the uh through WhatsApp group, right? For other regulation, I think you can refer to the final element lecture plan later on that I will upload. Okay. So, any comments or question before we begin with the first topic, overview of the finite element method? No? Okay. If no, let me continue. Okay. The first topic is overview of the finite element method. This is what I'm going to cover. First, I'm going to talk about mathematical models of structures, and then this is the core, right? What is finite element? Examples, the concepts, important concept in the finite element methods, okay? Discretization, basic elements, and then software, and then basic finite element computer steps. So let's start. Mathematical models of structures, okay? If you become an engineer, when you work, you have to do a design or to retrofit a structure or rehabilitation because maybe from earthquake and so on. Okay, what do we need to do? We need to what do we need to know or to understand when we doing, for example, design of, let's say, buildings? We need to understand what will be the building if subjected to some loadings, right? That load, life load, wind load, earthquakes. That's to understand the behavior of the structures, our structures, to external actions. Maybe not only physical mechanical holdings, maybe also due to temperature change, due to the movement of the soils, for example, settlement, differential settlement, and many others that we may consider, right? The question is how to understand a structure under a design process because the structure not yet exists. Or maybe another question is if this is not design work but retrofitting. Retrofitting, it means strengthening, for example, or rehabilitation. Rehabilitation, it means the structure has been in damaged condition and then you have to make it uh, to the initial, to the good condition, rehabilitation. And then you have to know the behavior of the structure, what to do, how to get the knowledge of the structure. There are three pillars of knowledge. First, direct observation, right? In the field, maybe you conduct an experiment directly to the building, or you use a physical model and then do experiment in the lab, okay? Or the third pillar is you can understand the behavior of a structure by computer simulation, right? So basically, to understand the behavior of structure, we may use simulation, computer simulation, or to perform experiment, or maybe direct observation in the field observations. Simulations actually based on mathematical models. What is mathematical model? Mathematical model is simplifications or idealization of the real structure. Okay, we have some assumptions behind a mathematical model, and then if this experiment we try to replicate condition of the structure, possibly on a small scale, and observe the behavior of the model. This is we use physical model. So our cost, of course, concerned with not this one. Our cost concerned with these parts. Okay, mathematical models. We use mathematical model to understand the behavior of real structure. Okay, here is an example. For example, we want to design a safety guardrail. Okay, road safety guardrail here. Maybe we propose some shape of the profile and then some thickness, and then we have to test its performance. Okay, like this. This is a video actually. Does it work? Oh, like that. Okay. These guardrails cannot be designed too strong. Why? If too strong, what happens? Ah, my slide is now doesn't work again. To the how can I make full slide again? Sometimes like this. Okay. I don't know why. What happened with my PowerPoint? Oh, it can. Okay. Uh, why we cannot make? Oh, I just choose very thick uh profile for this. Why? Can anyone have idea why? Because if too strong, yes, it's good. The car will not come cross to this area, come over cross to this crossing this area. But if the car hit, the car will be in serious problem because the damage may be very serious and may endanger uh, the driver. Okay, so usually, but of course cannot be too weak. If we have very thin profile, too weak, what happened? The guardrail doesn't effective, right? If a big car hit the guardrail and then just maybe the guardrail will break, just break, and then car move here, doesn't affect. So we should choose a stable, not too strong, not too soft. Okay. So, but the problem is when designing this, if we have to choose when we propose a design and then this time we have to do experiment like this, it's very dangerous, right? Not only dangerous but expensive. I mean, so in order to reduce the cost, okay, I propose some design and then we perform a computer simulation, but this doesn't work the video. Okay, computer simulation, okay, using a software. This is we can use software for simulation of this using, for example, LS Dyna. Okay, that's the benefits of simulation. Okay, well, so again, uh, when we perform a simulation in computer, it's based on mathematical model. Mathematical model for structures, or shortly a structural model. What is this? What is that? It's a formulation or a set of equations. So we have a set of equations, can be simple equations, or maybe can be complicated equations. For example, a set of partial differential equations, that's very complicated, right? The important thing is that these formulations express the essential features of the structure. Okay, so it's express the behavior of the structures or the process. Okay, the process of the how the structure deform and so on. In general, mathematical model can be represented as a functional relationship in the form of like this. We have some dependent variables, for example, displacement, bending moment, maybe shear force, as a function of independent variables. Normally, this the time and space and time of points, right? That independent variables, parameters, for example, material parameters, geometrical parameters, and forcing function can be mechanical force, temperature, and so on. Okay, that's mathematical function. So give a kind of relationship. So if we have some parameters, forcing function, dependent variables, we can determine the values of dependent variables. Well, in general, the mathematical model for structure we have two types of models. There's discrete models and continuous models. What's the difference? For discrete models, the displacement or the configuration in general can be exactly expressed using a finite number of degrees of freedom. So this is the keywords, finite number of degrees freedom. For example, if we have truss, this is undeformed configuration or initial configuration after we have some actions, uh, and then the truss deform to here. For example, due to mechanical force, deform to here. The configuration of the deformed truss can be exactly expressed in terms of this vector, right? If we specify this vector, we know this configuration. These vectors consist of two components. This displacement vector, horizontal, vertical. So we said that this truss has 2 degrees of freedom. So degrees of freedom is the number of independent parameters to express the configuration of structures. This is called discrete model. In contrast, continuous model, for continuous model, we have to express the configuration of a structure using infinite number. So this is finite, but this is infinite number of degrees freedom. For example, if we consider a beam in vibration, or maybe due to This is maybe a bridge, and then we have traffic lots, maybe a truck passing through the bridge, and then the bridge vibrates, right? How to express the vibration mathematically using a function. So the displacement at any point, for example, at the distance of x from the left, but not only function of x, but also function of time. So this is the vibration. Because this is continuous function of x, of course, we how many degrees freedom? For each point, we have degrees freedom. So it said that this model is continuous models. Okay, our finite element actually, yes, of course, can solve this. This is by nature already finite element already, but also we can the finite element in general is directed towards solution of continuous models. Okay, so to solve a continuous model, we can we have two ways. First, using analytical solution techniques. Second, using numerical solution techniques. Analytical solution techniques, it means we use maybe the methods from calculus to solve our equations. And the result is closed form solution, or we call exact solutions, right? Yes, this is ideal. This is good. Why? Because it's exact. The solution exact. There is no approximation. Unfortunately, for some models, it's difficult to obtain the closed form solutions, or even not difficult, but impossible because of the complexity of the problems. So normally this method only possible for simple geometries and boundary conditions. On the other hand, we have numerical solution techniques. Actually, there are many numerical solution techniques for solving mathematical models, such as finite difference methods. We convert differential equation to difference equation, right? Finite difference and finite element methods, boundary element methods, mass-free methods. But our course is this because this is the most widely used numerical methods for solving structural problems. Okay, so this is our course. Okay, can you give me a definition? What is finite element method from here? Anyone, please? Can you tell me what is finite element method?
It's a method to solve mathematical models.
Okay, correct. So we can define from here that finite element method is just a method for solving mathematical models of engineering problems using numerical solution techniques. That's a simple definition, and but it's correct. Okay, that's numerical techniques. Well, I'm going to talk a little bit about mathematical model. Right? This is the topic still mathematical model. For example, if we have simple structure, this is maybe steel truss like this, right? This is roof truss. This is the lower chord. This is the upper chord, and then this the diagonal members. Uh, Maybe we have connections here. Maybe can be bolted or welded connections here. The important thing is that when we have these structures, the joint may not be hinged, right? But we can idealize. It means we can make simplifications. This, for example, we model as hinge here, the joints. We call this model is truss model. Even though in reality, if we use welded connections, it's not hinge. It's a rigid connection actually. Or if you use high strength bolts with uh, pretension, it's also rigid connections. Okay, so this is actually idealization. Okay, idealization because idealization it means simplification. Okay, this rigid, but we model as hints. Is that any problem? Yes, maybe not so accurate, but it's enough for design normally, for design, class design, because if the loss here on the joints, if the loss only located at the joints, and we use this models, usually it's enough for design already. Of course, with the present computer, we can just model, oh, why not model just as rigid? Okay, it's better. Okay. But in the past, when manual computation is usually use manual computation, is we use simplified model. The second questions, is this model discrete or continuous? What do you think? This class model. Recall that it's discrete if it has a finite number of degrees freedom. It's continuous if it has infinite degrees freedom. What do you think? Finite or infinite degrees freedom? Okay, that's finite, right? Because we have 2 degrees freedom for each node, and we can count it, not infinite, right? So this is discrete model already. So in this model, we directly create a discrete model. So this is a process that from physical model to mathematical model by idealization and discretization at the same time. Because this is the we create a discrete model. Okay, so this is a simple example of mathematical model of structures. You know already, right? Okay, that's all. Any questions about mathematical models?
Sir,
Yes.
I want to ask, how how can we know uh the degrees of freedom? Like, uh, how can we know it's finite or infinite?
Oh, that's good question. Thank you. If we decide that our structure can move in certain only in certain ways like this, okay, only the nodes can move. We consider that the nodes can move, okay, but this bar cannot freely, for example, bend, okay, cannot bend just maybe extension or contraction. But the extension of contraction is already covered here, right? So it's discrete. However, if like the previous example here, well, for each point, we consider that it can move freely, independent of each other. That's make this model is has infinite degrees freedom. So also, that depend on our assumption, right? Uh, this is a matter of assumptions. We may assume that, oh, the structure just moves. The important motion maybe is just this one. There is no bending because we neglect the self weight and so on. Okay, so because of that, the important characteristic of this structure is just this one, this vector. So it's finite. This is infinite because its point we regard can move freely. Of course, if we can also say, oh, this is finite also. If we only consider maybe the possible motion only like this pattern, that's make our model finite. Okay, so it's a matter of assumption. Yeah, I assume that its point can move freely. But this one normally we assume that only this point moves, right? While the bar only, yes, there is extension and contraction, but and rotation like this. Cannot bend and so on. Any others? Can we proceed to yes?
So we can conclude that analysis using continuous models is far more accurate than discrete models. Am I right or wrong?
Right.
Or
In most
sorry.
more realistic, right? Because every structure actually consists of continuous uh, materials made from continuous materials. But of course, uh, mathematical model continue if you choose continuous model is difficult to solve. Okay,
Uh,
difficult to solve. So normally we resort to discrete because for discrete, that's finite element. Finite element is to make a continuous become discrete actually.
hmm.
Discretization method. Okay.
Okay.
Yes, more
Thank you.
accurate because it's more realistic. The more realistic the model, the more accurate. But usually the more complicated. Okay, let me proceed to this one. Well, finite element method or briefly FEM is a computational technique used to obtain approximate solution of engineering problem. I should emphasize approximate, not exact. In general, not exact. It means it doesn't equal to the exact solution of the continuous model that you use postform, right, or mathematical technique to obtain it. But later I will explain that we can improve the accuracy to the exact solutions. Well, that's the general definition. For us who have learned structural analysis before, what is finite element? It's a kind of follow-up method, right? Have you ever learned about directness method before? Have you learned directness method, DSM? Please tell me.
I think yes, sir.
In structural analysis too, right?
Yes, but I'm forgot, sir.
Oh, forgot. Don't worry, because we will review again in this course. Okay. So, well, for structural analyzer, finite element method can be regarded as a generalized direct method. Now there is no this course. In the past we have, uh, but direct method is normally also a finite element method, but applied to frame elements, frame structures. Okay, so for those who have been familiar with this method, I think you will realize that finite element method can be regarded as generalization of this method. Well, uh, the finite element method is originated as a method of structural analysis, but is now widely used in various disciplines such as heat transfer. It means to obtain the temperature distribution, how the heat flow in the body, right? Of fluid flow, seepage. Seepage it means the flow through soil, for example, electricity, magnetism, and others. Even now, the popular one of the popular application of the finite method is in biomechanics. Okay, biomechanics. So actually, not finite method is not only used in structural engineering, but also in many other disciplines for solving many different problems. Okay, let's talk a little bit about the history of this method. Modern FEM were first developed and applied by aeronautical engineers. That's Mr. Turner et al. And his colleagues. Who are his colleagues here? Professor Clough, Martin, and Top. So at that time, they work at Boeing company, and then they developed this method for solving a problem of airplane vibration, airplane wing. Okay, because you know when an airplane uh, in operation, we have to investigate it. We have to investigate to study the behavior of its wings. It's very important. Okay, So at the time they have difficulties to calculate the stiffness. So they come up with this method. This maybe can be considered as the first engineering finite element paper. Actually, before this, a mathematician current already uh, wrote a paper about solution method of torsional problems. The method is maybe considered can be a finite element as well, but that method uh, not popular because at the time there is no computer technology to apply that. So it's not by coincidence that finite element developed with the computer. Okay, because without computer, I think this method will not be popular. And then the name of the finite element method itself is coined by Professor Clough in 1960. Professor Clough is a professor at the University of California in Berkeley. He is one of the famous figure in the area of earthquake engineering. Okay, so if you have a book, Structural Dynamics, is by him, Clough and Pension, right? He gives the name finite. Why? In order to distinguish with infinite element in calculus. Because in calculus, if we take an element, very small element, and then we take the limit, right? Limit, for example, if we have this small element here, we call this is delta x, and then we take the limit delta x approaches zero, right? Both in differential calculus and integral calculus. We have that limit. That's called infinite small element. Here is not like that. We will not take limit. So we have a finite size. In 1967, uh, here appear the first textbooks by Professor Sienkiewicz. So this is one of the important figures in the finite element method because I think, these guys who popularize the finite element technology in civil engineering. Initially, this technology is in the uh, in the for those who are aeronautical engineers, okay, before civil engineers. Well, finite element method, the computation is carried out automatically using a computer or network, even a network of computers. Okay, so you can visit this YouTube video, I think, for later for a little bit more explanation about finite element method. But I think it is enough introduction, right? I will not go through to this video. So maybe you just summary. Finite element method is not for manual computation, but for computer application. Next, let's proceed to talk about how finite element used in practice. What do you think? So if you buy a software, okay, any software for structural analysis, let's say here Midas Gen, okay, and then you look at the website of Midas Gen, there is a kind of description, right, that this project use Midas. But what's the engine of Midas? What's inside Midas? This is made from Korea, I think, Korean software. Most of the software works based on finite element. For example, are you using SAP 2000 before? SEP 2000? How does it work? Do you know? It's the finite element there. Are you using ETABS? The finite element there. Minus? Yes. So if you want to uh, see a real application of finite element, just visit a software, a finite element based software websites. There they can talk much about application. Okay. Here just simple example from Midas. Also for, from other website, okay, GID, okay. Of course, finite element method is used daily in the analysis design buildings, also for studying, for example, the soil, this is soil and dam interaction, okay, for studying, for conducting research and for everyday design, okay. Also, even in designing the aircraft or maybe for rehabilitation of structures, just I mentioned before to understand the behavior of structure, okay, that's the application of finite element. So it's a widely used method applicable today. Any questions? So now you have give you now have an idea, right? What is finite element method?
Hey, sir. So there is
Yes,
something that I need to find out. You have mentioned before that in this class we use a discrete method, while when we use SIPRE tests, they use a partially different equation. So, is there any difference result? Because in partial different equation, we can find any bending or any detail different. So, is there any really difference between both of them?
you mean the difference result like that? Sorry, I did don't catch about the point of your questions. Uh,
In the
yes,
method that you mentioned before, we
yes,
don't separate any element to a small element.
right. We have a body, and then we divide it into smaller elements. Yes, and then
Is there any difference result because we don't put um don't make them to a small element
yes. Of
in
course,
finite?
there will be difference. There will be difference. Later we will talk about this topic. I think this is this topic, discretization. Okay.
Okay.
Well, as I mentioned, finite element is what is the function of finite element? What is the how finite element works? To make a continuum into discrete. That's called discretization, right? Continuous model to discrete. Okay. Practically, how to do discretization by dividing a continuum, I mean continuous body or structural system into a finite number, finite, not infinite, okay? Finite number of smaller and simple elements. Simple elements, it means in terms of geometry, you normally triangular or quadrilateral, whose unions approximates the geometry of the continuum. Maybe the unions not exactly equal to the original geometry, but approximates. This is true, especially if you have a curve boundaries, and then you have to model use a kind of polygon, right? The curves we model use polygon. That's we approximate the geometry. In doing this, we may have to do to create a mesh if this is two dimensional or three-dimensional bodies. And to perform a mesh, there is a specialist software GID, okay, called preprocessor software to assist us in doing meshing. Okay. Okay, example. What kind of model is this? Maybe it looks like a beam, right? But very short beam, a tapered beam. This is maybe in centimeter, for example, 44, 48, 16 centimeter, very short. This is continuum model. Why? Because we regard that each point can be moved freely, right? It has infinite number of degree freedom. And then we discretize using finite element. For example, this model. Okay. Now become a finite model. We create a mesh. For this mesh consists of elements. This is called quadrilateral elements. For each quadrilateral element, we have nodes. This is finite element nodes. Nodes is the location where the elements connect each other. So the elements is connected, not connected through along these edges, okay, but only connect through the nodes. That's important, okay. So nodes is the location where the elements can interact each other. There is no other interaction aside from the outside of the nodes. Okay, another example. Maybe we want to consider a circular plate. And
Excuse me, sir. Uh,
yes,
the
yes.
presentation is not on the screen right now.
Oh, doesn't appear.
Yeah,
Sorry.
yeah.
I think you accidentally stopped the share screen.
Oh, sorry. I pushed the wrong button. Yeah, let's present again. Can I hide this? Okay. Can you see all the slides?
Yes.
Yes, sir.
Okay. Second example of the discretization process. For example, I have a circular plates like this, and then we have some transversal loadings. Maybe they are fixed. And then for doing analysis, we can consider only a quarter path because of the symmetrical. We take advantage of the symmetric conditions. And then when we after we take the a quarter part, and then we create mesh. This is different with the previous one because we use triangular elements. Okay. Please notice that here is straight line, not a curve. So this is geometrical approximation. Circular curve is approximated by polygon, right? Here. That's geometric approximation. Well, I think this is relevant to the question from who before? Who asked question? Yes, this is the answer. The accuracy of the result, finite element result, okay, can be improved by two ways. First, using a finer mesh. It means we use a better mesh, more elements. That's called edge refinement. Edge is the symbol for the size, mesh size normally. Or using another method that's use higher order elements, OP refinement. P stands for polynomial, okay, because we use higher order polynomial degrees in the elements. You will understand better. Maybe you are still confused now, but I think uh, as we go on, I think you will understand what is P refinement. Okay, but for S refinement is easy to explain. Example, maybe I have presented this in my presentation in the workshop. Did you attend? This is the same example, right? For example, if I have structure like this, cooling tower, very tall cooling, and then we want to know the behavior, and then we use cell models like this, and then we create in SEP 2000. This is the mesh, okay? This is the possible mesh that we can create, and then this is the spots. The spots is only on at the nodes. This is called discretization because the structure is divided into smaller parts. This is called elements. And then after running the program, for example, here they use SEP 2000. Okay, who are they? Uh, they is it means Dodi and Andre. Who is Dodi? Dodi is the at the time my students, but now is my colleague. Okay, Pak Dodi. In 2008, still my students in the finite element class as well. Okay. Uh, and then this is the result. What is this? Oh, so colorful, so beautiful. But what is this? You can read in the legend. This is represent the numbers. Right? The red one watt, green, the yellow one is means zero. Okay. Okay, if we don't satisfy with these results, we can use finer mesh. Okay, like this. It means use smaller elements, use more spots, and then this the result we get. Now it's more clear, right, than before because we have now the red part in here. It means compression. The compressive part is not only here but also here. Here is tension. Here maybe almost zero stress and so on. Maybe this is due to the self weight of the only self weight of the structure. Actually, the important consideration also wind load maybe. Okay, but that's maybe we need to perform the analysis to determine the stress distribution due to wind loads for this structure. But please notice we can improve the result by make the edge is the element size smaller. So let's call edge refinement. Well, that's in 2D. Cell is basically 2D. This is another problem. This is taken from my previous student as well, who at that time doing the final project or scriptsy with me. In his scriptsy, he take this object and then use GID to create mesh. This is 3D body like this, and then use his own program. So he make he his own program to do this analysis. Okay, so that's one of my students in the past scriptsy with me, and then they do like this. This is 3D. So in general, this is the simple elements. I mean, depending on the problems, if the problem if 1D normally lines can be curve, okay, curve. No, this is 2D. Also, the edges can be curved. 2D, you normally triangles or quadrilateral. In 3D, we have some options like this. Tetrahedron, this is the simplest one. Hexahedron or wedge elements. Okay. Okay. Just a little bit about P refinement. Normally, geometrically, if we have triangle, for example, naturally the notch is here, right? The vertices, the notch is on vertices. But this is that the simplest one. We call this linear elements. Okay, linear elements of first order linear elements. The notch is always at the vertices, like this, like this, like this. But it's possible if we want to perform P refinement. Now about P refinement, we use higher order elements. For example, quadratic elements. Here, not only we have nodes at the vertices, but also at the mid sides of its edges, right? Mid node here also, here also. You can see in 3D also, okay? This is what quadratic elements. If you learn more. Well, in this course, I will not discuss these quadratic elements, but I discuss this element maybe in another course of finite elements that in uh, postgraduate or master program, right, for these elements. So my scope for this course is only this element, particularly this one and this one, okay? Maybe if we have time, we discuss this. Not really, only this one for this course. For postgraduate theory, I discuss this, okay? But this is not maybe because don't have time. Any questions? So now at least you have some idea about what is discretization. To make a continuous model become discrete. How? Using mesh, right? In mesh, there we have choice. We may use linear, or quadratic, or maybe we use triangular or quadrilateral. We have choice. It's up to us. Okay, up to availability the software as well. Any questions?
Sir,
Yes.
when modeling a spherical-like structure or curve-like structure, are the two-dimensional mesh elements were modeled as curve elements too, following the shape of sphere structure, or just a normal straight element that were inclined manually one by one to follow the structure manually?
So your question is to model a uh, curve-like structure, right?
Yeah.
And then depend on the software. Maybe if the availability of the elements, the software only straight line elements, for example, this one, okay, linear elements, we have no choice. We have to model the curve shapes using just polygon. But if the software have quadratic, actually this can be curved, the elements. We can move here outside and then become curve. Quadratic, because quadratic is parabolic curve actually. Okay. So if this is not parabolic, circular, of course, this is also approximation. Circular approximated by parabolic, different curve, but it's better than straight line. That's my answer.
Oh, so that can be curved like elements. Yeah.
Can be, but that's higher order elements. At least quadratic cannot be linear elements. Linear always become polygon like shape, polygonal like shape. Guess. Okay, let's talk a little bit about softwares. Uh, Currently, there are many software in the market. So this is just a few examples. Astran, ANSYS, Edina, Abacus. This is normally very expensive softwares used for research in finite domain, or yes, can be for industrial, maybe car industry. Okay, they use this one, but for civil engineers company, normally we use this, especially for buildings. This is very popular in Indonesia. Many structural engineers use items for because very convenient to design buildings, including not only analysis designs. Okay, because already design costs in here. Uh, Sans Pro is the cheapest one. Why? Because it's made in Indonesia. Actually, the one who made is Pak Nathan Madutuju. That's my senior in when I study in Parahyangan Catholic University in Bandung. Okay, he is my senior. Okay, so he who created this software. This is also very good software. This is quite expensive, right? If you want a cheap software but good, I think I recommend this Sans Pro. Okay, you can take a look at the websites on the software. I will not discuss the details, but you know, right? Just browsing the websites. For those who learn geotechnical techniques, the one that popular is this one. For those who doing research on earthquake engineering, maybe this popular, okay, software. All of this software, to some extent, use finite element. Okay. Of course, there are the aspect of computation such as for design. Okay, here we have, for example, in SEP 2000, we have also design costs, concrete design costs, steel design costs, what else? Aluminum, cord form, quite complete. So it's suitable for professional structural engineers. Okay, so already have many available softwares in the market. The question is, why do we need to study the basic theory? Why do we need to study the finite element method? Why not just buy the software and then relax, learn to use it, and then use it? That's the question, right? Oh, because of academic requirements. No, you don't have to take it, right? But okay, here is the answer. Okay, uh, Cook and his colleagues said that concepts and assumptions behind the computer codes, that's finite element software should be mastered. Engineers are expected to be able to use the software to gain better advantages and will less likely misuse them. Okay, if you don't have any idea of what is going on in the software at all, that's dangerous, right? It's easily to misuse the software. So by learning finite element is one way to know what's behind the software, what's going on behind the software, right? So if you maybe find the software doesn't work for some reasons, you will have more, you will likely more have any knowledge or any knowledge to how to fix it. Okay, let's now take a look from the pop software that I think you know already, SAP 2000 disclaimer. The user accepts and understands that no warranty is expressed or implied by the developers or the distributors on the accuracy or reliability of the program. Oh, this is important disclaimer, right? The user accepts, understand. No warranty, no warranty. So the users must explicitly understand the assumption. Again, when you use software, you must explicitly understand the assumptions of the program. Even you have to independently verify the results. So again, this course will help you to understand the assumptions. So when you use any finite element software, you will have background knowledge. Okay, background knowledge. Not all, of course, not all. It's impossible to cover all because finite element is very huge uh, area, but at least some basic knowledge through this course. That's my hope. So you can use software better as a professional engineers. Well, long discussion, quite long discussion. Any questions? Okay, let's proceed to more details. What's the common steps for the static analysis? So our course will cover only static analysis because linear static analysis, because actually finite element can be applied to dynamic analysis as well. Like in the lecture of Pak Ben, structural dynamics, earthquake engineering can be applied, or even to nonlinear analysis can be applied. But our course, because this is the course for the first time learner, right? We are going to focus on linear static analysis only. Here is the main steps of the finite element procedure. First, as you know already, if we have a continuum, discretize it, mesh it, okay? Create a mesh. And then after the structure has been discretized, the next computer steps faithfully follow the steps in the directives method. The question is, what is directives method? The directives method is a method where the global discrete equations can be obtained by assembling the elements contributions, assembling in a direct manner. So it's called direct because directly at the contribution from its elements, right? That directives method. So that's why finite element is kind of generalization of directives method, because the important application, important implementation of the finite element method is the DSM directives method. Okay. Well, this is the for-state linear static analysis. Uh, Actually, we will create global equations. The global equation consists of the stiffness matrix, the global stiffness matrix, and then the displacement vector. So, and then equals to the force vector. So this is the steps, okay, to obtain that equation. First, generate element stiffness matrix and element force matrix for each element. So if we have structure, we have already discretized using some elements, several elements, and then when we perform running SAP 2000, for example, what's going inside? They will compute stiffness matrix, element force matrix for each element, and then assemble, add them together to obtain the global stiffness equations, and then apply the loads and the nodes, and then apply the boundary condition, and then solve it. Okay, so we will have nodal displacement. Okay, after the solution, we will have nodal parameters or displacement. Once we have displacements, actually we have passed through the major steps in the finite element. Then subsequent steps are called post-processing steps to obtain the internal forces, for example, bending moments, etc., or internal stress. That's the static analysis going on. Okay, this is the global steps. These global steps, I think we will carry out manually later. We will go over by examples of the problems in the context of from the simplest one is spring system. Okay, but this is the general computational steps of the direct test method. Any questions? That's all about the overview of the fundamental method. You can read further in my book, right? The chapter one of my book I already give to you in the WhatsApp group. The first chapter, I think the same topic with this one. What's next? Next, we are going to learn the direct test method. The direct test method we will apply beginning from the simplest system, that spring system, okay, like this. But before that, any questions? And what's the time now? Do we still have time? I think yes, right? 15 minutes. Do I move too fast?
No, sir.
No, okay. I think
Maybe
yes.
I want to ask. Can you explain about what is the meaning of the color when mesh is created up and then the mesh is being analyzed and
Oh,
then
okay,
it
okay. The
generates.
meaning of color. Okay, okay, okay. You refer to this maybe this example, right?
Yes.
Depend on the model, of course. This is cells. If we talk about cell, uh, what we expect from our analysis, static analysis, let's say, we expect that we want to know the membrane forces. The membrane force, it means the in-plane force. If you attended my workshop, I explained that. Okay, in-plane force. There are two types of in-plane force. One is tension or compression. The other is shear. Here that I shown here is the I think the in-plane force in-plane in vertical direction. Okay, maybe in vertical direction. And then the meaning is that here is the distribution of the membrane force is quite high. What the value? This is the value, right? Minus, not so clear, maybe minus 1 point something. Oh, okay, that's the meaning. In what unit? Of course, you said you have to see the what unit. Okay, maybe kilonewton per meter or S. Because when we use software, we should be careful, very, very careful with the unit. What kind of unit? Okay, this is has unit. So the meaning of its color, it means distribution. The red, it means that this part is highly compressive because this is minus. Not normally for cells, minus is mean compressive force in vertical direction, but this is no almost no force, internal force. Green is tension because this is positive. That's the meaning. Okay, depend on what kind of if you perform a structural analysis and then this is bending moment. What is bending moment? Distribution, right? Distribution bending moment. But here for this 2D structures, we use instead of graphs, we use color contour. This is color contour. okay, of the results for
Uh,
cells.
it means vertical planes or horizontal planes, sir?
Vertical. This is, I think, vertical. Vertical membrane force. Okay,
Okay.
in this direction. Because we can show also another option here. Okay, shear in the software. This is just to illustrate that we can perform refinement, right? As refinement. Of course, you have to understand this. You have to understand the theory of cells, at least the basic things of cells. Also, this one. What's this? Oh, this is color of not so clear. What is stress? Shear stress maybe. SXY. Okay, so it means high stress, high shear stress in here. In the part that meets this one, right? And this block. Normally, high stress region is dangerous. The weakest part of the structure. So we should be careful. That's the why we perform this analysis.
Okay, thank you, sir.
Any questions, however? Okay,
Sir,
let me, yes, okay.
I
Nathanael.
want to ask you, can you please re-explain about how by creating mesh can discrete a continuous model?
Okay, good questions. Okay, can you see the screen?
Yes, sir.
Okay. Let's say we have a plate structure, right? For example, like this. So this is routine. And then we have to discretize. Let me show in the top view like this. Okay. If we have some loadings here, it's continuous model because the deflection of the plate, I don't know how to draw it. Okay, maybe like this is free, right? For its knots, for its points. Here we have deflections. We can assume freely deformed. But this is continuous model. How to discretize using finite element? We choose in our software, for example, to divide this into several quadrilateral elements. Let's say like this. And then this is nodes, finite element nodes. Let's say for nodes elements. Okay, each element have nodes. What does it mean nodes? Nodes it means the location where we define finite element displacement. It means when we come to the reality here, by creating finite element mesh, okay, it means the displacement is only allowable here, okay, for its nodes, not every point. Because of that, become discrete model, a discrete model. Because not every point can move freely. Only the finite element nodes can move. A kind of restriction to the original model. Is this answer your questions? I think the time is up now. I think already quite late. But thank you. I will not proceed because I also feel tired after the conference. Maybe next week we will start on time, and then we will directly proceed to the details computation of direct method. Okay. All teaching materials I will provide in the cloud Lentera. Okay, see you next week.